Welcome to the 5th WIPAC webinar, this time talking about controlling the activated sludge process. My name is Oliver Griefson, Technical Lead for the Water Industry at ZTech Control Systems and Executive Director at Water Industry Process Automation and Control. We're kindly hosted today by Wastewater Education, a US charity designed to spread knowledge about the wastewater industry. We're joined today by 5 fantastic speakers from around the world. These speakers include Leiv Rieger of inCTRL Solutions, Stuart Ainsworth of Hach, Mikkel Dooley of Strathkelvin Instruments, Mikkel Holmen Andersen of Unisense Environment, and Jordan Schmidt of Lumen Ultra, all talking about different aspects of ASP measurement and control. Our first speaker is Leiv Rieger, who is the Chief Executive Officer at inCTRL Solutions. Leiv is a well-respected expert from around the world in activated sludge plant control, and he's going to speak to us about the basic process control fundamentals and how an understanding of the system leads to better controller design, which of course leads to better performance of the activated sludge plant system. So without further ado, I'll introduce Leiv and let him take over.
Thanks, Oliver. Nice introduction. So I'm the first in a line of quite a noted speaker, so I have the highest chance of messing up your schedule. So let's jump right into that. I'm not quite sure how to move my slides. Okay, that seems to work. So what I would like to talk about today is about process control fundamentals, and I throw in quite a number of process fundamentals as well, and then I apply that to an example which is ammonia-based aeration control. So unfortunately for SRD control that I would need a little bit more time, so I don't go into details there, but happy to answer any questions. Good, so let's jump right into control fundamentals. So there are 2 basic principles for control loops, and the classic one really is feedback control, typically executed or implemented in the form of a PID controller. I also don't go into the details and the math and all the tricky parts here. So the feedback control really is that you want to control a certain variable and you define a set point here. And then, of course, you want to make sure that your control variable is around the set point. So the special thing here is that you measure the process response, right? So that's quite important to understand. That means you don't fully have to understand what's going on inside the process because you measure the controlled variable coming out, so the response. The other concept is feed-forward control, right? So you still have a controlled variable and you still want to maintain that variable around a certain set point, but you are actually measuring the disturbances. So what is impacting the process? Yeah. So very important to understand that if you measure the disturbance, you are much faster, right? So you get information on what may impact your process early on, but you need a model, right? Because you're not knowing what comes out and how the process actually reacts. So you need a model of the system, and you can keep that very simple, but right, so the better the model, the more accurate your control decisions. The more accurate, typically the more complex, and that means typically you need more sensors. And it's still a model, so you need certain safety margins to protect your effluent in the case of wastewater treatment. So much faster. So there are situations where you have to do that, where a feedback controller would fail, but you need a model, and I would say you must always complement that by a feedback signal. I think we will learn about that later on. So feedback signal can be that you run a model where you recalibrate or you combine that with a feedback controller. Yeah. So in wastewater treatment, I would say most of the applications feedback control would be sufficient, but there are certain cases where it would make sense to go for feed forward. Okay, so this is a slightly different description or visualization, quite simplified here. So this is the DO controller, DO set point, and controlled variable. And typically you calculate the difference between the two as an error, and then you apply your control logic on it. Yeah. So the output, so the controller output, what the controller calculates, we call manipulated variable, and important are these upper and lower bounds, right? And we will learn about them later in that presentation. At the bottom, this is how we visualize. So visualization is very, very important because the operators have to understand if the system works or not and what the system is doing. So it helps you a lot in maintaining that in operation. So what we typically do is we plot the set point and the controlled variable on the left-hand side. They have the unit, the same unit. That's very easy. And on the right-hand side, manipulated variables and the controller bounds. So very important is in the end that if you are hitting a bound, and the bounds are to protect your process and your equipment, if you are hitting a bound, your controller is off. Yeah? So, oh, I have a bad echo right now. Okay, that's better. So very important to realize, if you check controller performance, if you're hitting a bound, that controller is actually not doing anything. It's just sitting on the bound. Good. So to make it a little bit more complex, we discussed a single control loop implementation, and now this is an implementation of an ammonia-based aeration controller, and we see that this is done in form of a cascade, right? So you have, that is the ammonia control loop. The ammonia control loop calculates a DO set point, which is picked up by the DO controller, and then there's an airflow set point, and the airflow controller then calculates a valve position, and then you have typically something to set, sort of a valve positioner to actually execute that control action, right? So a full cascade. Yeah. So to make it even more complex, this is just one control loop, right? Or one controller. So if you have multiple aeration grids, controlled aeration grids, then this adds, so doubles or triples or whatever the number of controls. Then you may have multiple trains, and keep in mind that is all only air distribution control. You also have the air supply control, or in other words, the blower controls. Yeah, so it becomes quite complex. And the way we deal with that complexity is that we put all of that into a model, modeling everything from the blowers, blower control, maybe most open valve control, the main headers, basin headers, drop legs, manifolds, laterals, up to the diffusers, which is the connection with the process, and then of course also the DO and airflow controls. If you model something successfully, of course, then you fully understand the system. Yeah, so this is the way we design or customize control solutions, having a more holistic view on things, and we actually combine that with a process model, allowing us to have all kinds of influence and temperature scenarios. We include operational changes. We can even model equipment or sensor failures. We model the sensors with the response times and the noise. Very detailed models of the control system. This is a one-to-one implementation in the model compared to what you would have at the plant. Equipment models I showed before, and you can even do cost calculations. Yeah, so very important. If you want to take the risk out of commissioning, do that upfront. and you know what will happen, and you have a much more holistic view on things. So brief procedure we apply when we set up a control system. We start with defining process goals with our clients, right? And very important is to prioritize these goals. I will walk you through an example, so ammonia-based aeration control later on, to make it easier to understand, right? So right now that's process goals. And then the most important step in control system design is translating the process goals into control goals, right? So that has to do with defining what you measure and what the actuators are. Yeah. Then we want to identify any process and equipment limitations. I'll discuss that with the example of ammonia-based aeration control. Then we go into the designing the control structure. If we use PI, PID controllers, any model-based control, and so on. Yeah, and then setting bounds, very important to set the right bounds, and then of course tuning of the control loops. So let's jump into that example, and specifically into process limitations. Yeah, so that is very important to understand for ammonia-based aeration control. Most of the control systems I saw failing, people didn't have a proper understanding of process and equipment constraints, right? So the first one for ammonia control really is a kinetic constraint, meaning if you reach DO of, let's say, 2 milligram per liter in, so a qualifier is in all sections of the plant, right? So not only where you measure DO, then more DO is not helping. So increasing aeration intensity, sending more air into the tank will have no impact, right? And that's very important. Ammonia control is very powerful in the other direction. So if you switch off the air completely, there is no aeration, nitrification left, right? However, if you increase, there is a limit. It's saturating and more air is not helping. Very important to design that or in the design stage. The other one, so that is even less understood, is there is a constraint or a process limitation coming from the mass of the organisms, in our case, the nitrifiers, right? So the mass of nitrifiers in your system depends on the average load, let's say, the 2 weeks before, right? So that depends on the sludge retention time you're running. So that means that you have a certain mass of active nitrifiers, and at times you overload that or you underload. And you have to understand that your controller manipulating aeration, so aeration intensity, has no power to overcome that limitation. Yeah, very important to understand. You would have to go outside that control system, change the sludge retention time. So the higher the sludge retention time, the lower these ammonia breakthroughs, for example. And then if you control sludge retention time, typically the problem is that at a certain point you cannot go higher with the mixed liquor suspended solids because your clarifiers are limiting. Good. So important is that you understand your process before you start designing a control system. So now into equipment limitations. And for ammonia-based aeration control, we typically have these 4 main limitations. The first one is diffuser distribution and valve sizing. And basically that defines your air distribution within, right? And it also defines it in places where you don't measure DO, right? So you don't know what's going on. So it's quite tricky to understand. So one message here is a bad design of your aeration system can break your control, or in other words, the best control in the world would not be able to overcome that. The other one is blower capacity. For ammonia-based aeration control, it's the downturn, so the minimum. Airflow for mixing, you want to maintain that, of course. And then diffuser specs, so airflow per diffuser. Be careful, for example, with ceramic diffusers, you can destroy them if you are going lower than the minimum. Yeah. Good. So important here is that all the parts have to work together, and that means process, equipment, sensors, and the controls. Right? In my opinion, the only way to really figure that out is to put that into a very detailed model, and we are using Sigma Sharp for that. Okay, so that's now the example with the process goals and translating that into control goals. So if we discuss with clients, there's typically a whole list of things they want to achieve with that control, and we moderate that discussion and then help them setting priorities. So typically for ammonia-based aeration control, the first thing is save energy. If we translate that into a control goal, that is that we want to vary the aeration intensity to maintain an ammonia set point. So that means we have to measure ammonia, and we have to make sure that we somehow can manipulate the aeration intensity. So that all is to reduce nitrification. So we are limiting nitrification, and that saves us energy. Yeah. Good. So the next one we sometimes hear is reduce ammonia effluent peaks. So this is something which is a bit tricky. So again, so increasing aeration intensity has its limit. If you reach 2, there's nothing happening anymore. So you should actually switch to a different control handle, which is increasing the mass of active nitrifiers. And that is typically done by using swing zones. Swing zones control is quite tricky, so I would be very, very careful and model that up front. It's not that straightforward. The next one, maybe increase total nitrogen removal, or let's say increase denitrification. And there, it's a question of priority. So if it's second priority, I would just leave it up to the ammonia controller. So you lower the DO and you will introduce simultaneous nitrification, denitrification. So you increase total nitrogen removal as a side effect, right? So if you want to have that as a priority, you would set that up differently. Yeah. BioP performance, same thing. You can see that as a side effect. If that is the main focus, then you have to design a specific control solution for that. And typically the plant will tell us that, of course, we have to maintain our permit. That's correct. Yeah? So we all want that. The question is, how comfortable are they to, let's say, have ammonia breakthroughs? What extent? And of course, the safety margin. So that, let's say the permit is written as a daily average. Then how far away do you want to stay from the permit? Yeah. So you have to discuss that with the client and make sure you're all on the same page, and to be able to include that in your design. So the tricky bit here is that reduce ammonia effluent peaks. If you change, let's say, the swing zone operation, that's a different actuator than aeration intensity. Yeah, so these are independent controls, shouldn't be completely independent, so you have to coordinate them, that they are not fighting each other. But basically you use different actuators, and you have to keep that in mind, that it's not just one does it all. Yeah. So the classic ammonia-based aeration control implementation, and this is the standard we are doing most of the time, is that we have a cascade ammonia DO airflow. Ammonia typically measured at the end of the tank. Then DO, rule of thumb is 1/3 downstream from the head of the tank, but we would refine that based on the model, because it heavily depends on the diffuser distribution. And then airflow you would measure per controlled zone. There are other aerobic implementations, for example, direct ammonia-based aeration control, so ammonia directly on valve position or airflow loop. I would clearly not recommend that. Very difficult to tune, not protected against high ammonia loads, and it's just not the correct setup, I would say. Feed-forward, feedback combination, in my experience, typically not required. There are certain cases where it makes sense, but then use a different actuator. So, for example, swing zones to have that impact you need. Keep in mind that typically increases cost because you need more sensors you have to maintain, complexity increases, and you have to also maintain your model. Yeah. Same with model-based predictive models. Due to cost and complexity, I see that rather for larger plants, right? So that is quite tricky to set up and maintain. I don't see that the cost-benefit analysis would be positive for smaller plants. Okay, so feed-forward control makes sense if there's a problem with how fast the system reacts to changes. Typically, in my experience, there is none, or you have to work on other things to mitigate that and keep that control system simpler. Okay, so commissioning operation. If you want to actually sustainably operate that control system, and I would count ammonia-based aeration control and SRT control into advanced control already. Most plants will not have an easy time with that. Most important, and you see that in all 4 boxes, is visualization. Make sure that the operators get information on how it works. A big thing is maintenance and quality control, and then you want to monitor equipment and the process. You want to know what the process is doing, of course, any special event. And then you want to link that to the control system. So we have developed a number of controller performance metrics to be able to monitor that at all times, indicating if better tuning would improve performance, right? So that's very important to understand. Tuning is not helping all the time. So if the controller is sitting at a bound, the best tuning would not improve, right? Because the controller is not active at all. So sometimes you have to go outside your controlled system and change the sludge retention time, for example. Yeah? A couple of examples before I wrap up. So this is our standard controller monitoring view. So you see the controller cascade here, indicating something is wrong. So that is actually bad tuning here. And this is the actual situation and the actual measurements here. That is very helpful, or proved very helpful, to provide information to the operators what control structure they have, right? So it's the hidden technology. So if it works, nobody knows how the DO is controlled. Bringing that to light is very important. And then they have the option to actually check every single control loop. And at the bottom, you see again, so this is the green is the set point, blue is the controlled variable, in this case ammonia, and black is the manipulated variable. Not well performing, so you see that bad. This actually tells me that with better tuning, you would improve the performance of that system. Yeah, so visualization is very, very important to make the system, control system, work after commissioning and not just switched off. Yeah. Sensors, right? So you need to make sure that your sensors provide the right results. Here you can see that's an ammonia analyzer, and we fully had that thing under control. Very good instrument, and actually it works. We also organize maintenance in that implementation. That's Grand Rapids in Michigan in the US. So this is more advanced. That's a detailed analysis in auto-tuning. In blue, the current settings, green, the calculated ones by our, so it's a model-based auto-tuning system. And then you can see the improvement in that controller metric or controller performance metric. And again, visualization that you see what's happening. Yeah. Good. So take home message. So if you go into controller design, start with a clear objective, right? Only then can you translate that into process goals, control goals. You need to understand the process and equipment limitations. And in the end, in my opinion, the only way really is to put everything together: process, equipment, sensors, process, and the controls, right? So if you put everything together, you fully understand that, and then you take out the risk out of commissioning. Good. Maintenance, you have to get the different parts under control. So we do monitoring of sensors, process equipment, and the controllers. And again, I repeat that maybe not even often enough, visualization is key. So if you, maybe not even often enough, visualization is key. So if you recognize all that, control is actually providing lots of benefits. You're dealing with the inherent dynamics of your system, and you can just get more out of your treatment plant, right? So you improve the water quality, and you can also save on or reduce resources, and you also increase the resilience of your system. Okay, with that, I'm done and happy to take.
So thank you very much for that, Leiv. We've got one question from Laurie Reynolds whilst I load up the next presentation. How many plants are operating under the inCTRL models?
We use the models first for the design, right? It doesn't mean that we are using the models for the control or in operation. So these are two different things. So I wouldn't know. So we designed or troubleshooted a lot control systems. So the last study we finished just a couple of weeks ago was the city of Toronto, one of the largest plants in North America. We worked Denver Metro, Los Angeles County, Fort Worth. Yeah, so that's a long list of plants. So the platform is under development. So we have a full-scale implementation in Grand Rapids in Michigan. So that's the first generation. And currently we are testing the new generation in Germany and the US.
Okay, thank you. I hope that's answered your question, Laurie.
Some more.
Well, maybe not. Harry, did you have a question? Here we go from Harry. Are some plants only using ammonia or DO sensors, or are all sites using both?
There are some plants only using ammonia, but I would strongly recommend not doing that. So multiple reasons. One is that the fallback strategy for me is DO control, right? So we have to make sure that, let's say, the ammonia sensor analyzer fails or is under maintenance, you have to switch to something else, right? And I typically like to go to the underlying DO control system. That's what the operators are used to. And then you're using as a fallback a controller which is active all the time, right? So that makes it much easier. Also, if you have very high ammonia concentrations and you're running into a limit, if you're not using DO, you will heavily overrate. So that system is I wouldn't recommend doing that. But of course, there are plenty of plans.
Next question from our next speaker, funny enough. What are your views on artificial intelligence to build models?
I don't like the terminology. So artificial intelligence, what people call artificial intelligence, for me, it's just pure math. We call that data-driven models. We use that a lot, right? So we have one team focusing on data-driven modeling and data analytics. Very, very helpful. If you are running models at all times, then typically the data-driven models are more robust than the mechanistic models, right? So that has to do that data-driven models can take into account all the variables, right? So input, output, in reactor, everything, pictures. So they are typically more robust, and they provide the ability to use diagnostics. Yeah, so self-diagnosis is very important. These models will, if properly set up, will tell you that they don't work anymore, right? And mechanistic models, to be honest, the only thing they do is provide more data. So you still need an expert knowing where to look. Yeah. So in general, data-driven models, there is a huge market. We actually use hybrid approaches. We prepare the data using data-driven models for cleanup and augmentation, feed that into mechanistic models. And
thank you for that, Leiv. Our next speaker is Stuart Ainsworth, who is an application development manager at Hach and a well-respected international expert in real-time control. Stuart is going to talk about applying dynamic swing zones using a model-based approach. So at that, I'll let Stuart take over and give his presentation. Thank you, Stuart.
Thank you, Oliver. Yeah, so today I just want to talk about one of our many applications, really. So basically, kind of touching on what Leiv mentioned before, which is applying swing zones to activated sludge plants using a model-based approach. So today, what I want to go through is just some of our experience since we've been in the control business. The typical process challenges we see around achieving low total nitrogen limits. General approach that Hach has, and try and apply some of the logic or try and outline some of the logic that we use to build out our solutions. And then specifically talking about a case study, a UK-based study, which is kind of how the swing zone development came about in the first place. Okay. So in terms of our experience, I know Mikkel Heck is on the line as well, and Mikkel's the grandfather of real-time control from a Hach perspective. So we've provided real-time control solutions for over 10 years now, about 12 years it is. And from the start, we've been using model-based control systems. So ammonia-based aeration-based control based on ammonia measurements. So over that period of time, we've got over 600 applications across Europe and North America. And yeah, we've got we can see that the rate of acceleration in which we're providing these systems is increasing as the quality drivers push for stricter and stricter total nitrogen limits. And in a UK perspective, there's also low phosphorus on the horizon. So we think that the alkalinity recovery associated with denitrification is going to be an interesting story for the UK plants in the future, because obviously there are very few sensitive waters for total nitrogen around the UK, but I think alkalinity availability is going to become a much bigger story in the coming years. So just talking about some of the process challenges that we see around meeting total nitrogen. First and foremost, we see excessive oxygen in the anoxic zone, which is obviously a problem. So yeah, typically that's because of carryover from the return activated sludge, or it can be that that the actual the set points have been too high in the first place, and then you remove so much load that you get excessive DO in the back of the activated sludge plant. So first and foremost, check if your anoxic zone is actually an anoxic zone or not. And Leiv touched on this before, sludge age control. So it's incredible that sludge age control isn't employed more in the industry. So relying on operational staff to calculate the sludge age and to make adjustments and to do that in real time seems a big ask, really, for me. I would encourage anybody with an activated sludge plant to first start with sludge age control, because when you're matching the sludge age to the sewage temperature, you can be sure that you're driving the right amount of nitrifiers within your basin. And if you get your sludge age right and you get the aeration conditions right, then, and obviously your plant's been designed right in the first place, then that's 9/10 of the battle. Often we see storm events pushing high ammonia loads, so breaching total nitrogen because of an ammonia spike event. And again, coming back to the most common approach of having a fixed DO set point for carbonaceous and for nitrifying plants, then we see time and time again that there are typical weather events or or specific industrial load events that can push load through, which results in high nitrogen, either in the form of nitrate or in the form of ammonia. Other problems that we see is just the sparsity of the data. So typically an operator will know about that problem when there's a regulatory sample or when the sample comes back from the laboratory. By having online data, quality online data, the operator's in a much, much better position to actually make a meaningful decision. Still an incredibly challenging thing to do in terms of introducing a swing zone or delivering the right DO set point. That's still an incredibly challenging thing to do manually. That's where our systems and other model-based systems come into the fore to actually apply the right level of treatment at the right time. And obviously, alkalinity is is going to be a big ticket item for sites with low phosphorus limits, and they're being applied across the whole of Europe in the coming years. So even if you're not interested in having low total nitrogen being released to the environment, the alkalinity that you can harvest and the oxygen value of nitrate that you can harvest to improve the efficiency of your activated sludge plant is it's a huge benefit that is available to most plants by either retrofitting swing zones or by enhancing the existing anoxic zone that you may have. Obviously, sometimes we see inhibition, and we can recognize that as part of our control structure. And another failing point or another area of optimization can be improving the internal recirculation strategy. So often you just see a fixed speed, which doesn't recognize the amount of nitrate that you're returning, or in fact, if the DO levels are elevated, and you'd be better to really crank back the internal recirculation flow. So they're the typical problems that we see when we're looking to optimize and make a plant more efficient. And I just want to put the swing zone in context of what we offer in terms of our control suite. So what we have is basically an off-the-shelf product. So we want to make advanced control as accessible as possible. So we've got specific controllers for industrial applications like dissolved earth flotation or nutrient balancing into an activated sludge plant. We've got sludge applications around sludge thickening and sludge dewatering. We've got 5 separate approaches, more than 5 actually, for phosphorus removal. And we've got, if you've got a specific problem or a very unique problem, we've still got the capability to design an in-house bespoke solution. But that, we enjoy those, but our main driver is to make buying a control structure as simple as buying an ammonia measurement, for example. So they're the outside the activated sludge options. Within the activated sludge options, we've got a suite of off-the-shelf modules for simultaneous nitrification, denitrification. So basically carousel oxidation ditches or carousels. So that gets away from the problem of delivering a DO set point when you've got a DO gradient across the volume. We've got specific options around intermittently aerated activated sludge plants. So again, that's based predominantly on a feedback. That doesn't use a model. It's measuring within the treatment basin on a feedback control structure. But in the case of constantly aerated plug flow activated sludge plants, we have got a model-based approach. So in terms of that type of activated sludge plant, we've got specific control for sludge retention time, for the nitrification element, and for the denitrification element. So we've got, and in terms of denitrification, that can be methanol addition, it could be the recirc rates of the internal recirculation. We've got swing zone, which is what I'm going to talk about today. We've also got most open valves. So that allows us, again, we've got an off-the-shelf solution to optimize the aeration system. So that's, again, it's too big a topic for the slot that we've got today. And I've put nutrient addition as well. So if you've got an activated sludge plant which is nutrient limited, we've got automatic methods to make sure that the NMP availability is optimal to make sure that you achieve full treatment. So that's kind of this is where swing zone fits into our whole suite of offerings. Okay. So how do we incorporate swing zone into our model-based control? So unlike the previous example, which uses one ammonia measurement with a model and a feedback zone, we always employ two measurements. So we always have a measurement at the inlet of the activated sludge plant and always have a measurement at the outlet of the activated sludge plant. So the measurement at the inlet of the activated sludge plant, allied with temperature, the sludge age to determine how many nitrifiers we've got present, the mixed liquor suspended solids to dictate how much biology we've got there in the first place, and understanding the size of the tank and the residence time of the tank, we can use that to provide a feed forward intelligent dissolved oxygen set point. We then modify that set point based on a true measurement. So we've got we've got an enormous amount of data which demonstrates that our feed forward approaches are accurate. Where there might be variations from what we expect, then we automatically adjust to take that into account. So most people will tell you that their activated sludge plants have got completely even flow across all the lanes or trains. And if you really dig into it, you can see there are some really big issues around flow distribution on certain plants. Also, if you look at when you're delivering a dynamic DO set point, you can really expose some of the fragilities of the existing DO control as well, which is one of the reasons we developed our MOV controller, because we were kind of hamstrung by other control strategies for aeration control. So we took it upon ourselves to improve the DO control to make sure that the plant can actually respond to our DO set point. Okay, so that's our model to deliver the correct DO set point for nitrification. In terms of denitrification, we can use a nitrate measurement probe at the end of the anoxic zone, and then that will inform whether we need to add more carbon or whether we need to increase or decrease the internal recirculation flows. So in addition to that, what the power of having a measurement upstream of the activated sludge plant is, you then know the true load conditions that you're presenting to the activated sludge plant. And when you know the true load conditions, and when you know how much biology you've got within the aeration basin, you can then perform a calculation to automatically know if you can safely sacrifice some of the aerated volume to extend the denitrification zone. So that's effectively what we're doing. Our controller is always asking, can I reduce my aeration volume safely? And is the result of that reduction in aeration volume acceptable to the amount of treatment available? And at first, we had set points around sort of kilograms per hour of ammonium treated, which was very difficult for the operators to understand. So we've kind of flipped that round. So now the operator sets an aeration limit. So if we sacrifice the aeration volume at the head of the activated sludge plant and the resulting calculated DO set points fall outside the range that the operator wants the plant to operate with, then that will inhibit and that will stop it. So by switching from a kilograms per hour or a treatment rate, which is not something that operators carry in their head, to just does the resultant sacrifice of volume still allow us to safely operate within the operational window that you set? That is a much more meaningful way for the customers to optimize the system and to be able to parameterize it in a way that's acceptable to them. So just looking at the case study itself, this is a site in southern water. You can see that there is not a lot of space on this plant. So if you look at the bottom right corner, the first box that you see at the bottom is a 3-lane activated sludge plant. That was the original plant, and that was only designed for carbonaceous treatment. So we worked in conjunction with Stantec, who used a modelling tool to determine whether they'd be able to essentially squeeze a small enough plant on there and still achieve the total nitrogen limits. So they ran the model and calibrated it with the lab data that they had, and we had confidence, Stantec had confidence, and the water company had confidence that this was the right solution for them, because they were very keen to avoid methanol dosing, understandably, and they wanted to squeeze every last meter of space and every bit of value they could out of their available land. So that was one of the reasons that they reached out to us to intensify and safely provide the right level of treatment. So the start of the solution that we provided was our nitrification controller, so delivering intelligent DO set points to maximize the treatment. What we were also able to do was to run with lower DO set points at the back end of the plant. So we were intensifying the treatment in the first part of the activated sludge plant to give us the freedom to run with lower DO set points at the back of the plant. That'll enable us to ensure that the internal recirculation flow had low levels of dissolved oxygen, and we were maximizing the performance of the system. And we informed the internal recirculation flow by nitrate measurements in each of those lanes. So if you look at the lane there, that then sort of extends. So instead of it being just basically, it's turned to a 3-lane, 4-zone activated sludge plant. And normally that would have been enough to get us past the post, but in this particular case, some of the work that went on at the same time with the return activated sludge meant that there was air being entrained into the RAS. So we were actually, the actual plant behavior diverged from the modeled behavior because of this introduced air into the system. So we were all kind of scratching our heads for a little while to sort of say, well, how can we do this? So a number of features were done. There were some hydraulic changes done to the RAS well to try and minimize that, but there was still being entrained. So we looked really what we could do, and we made sure that there was still available treatment, well, we looked to see if we extended the time, would we get further denitrification taking place? So that was the point of the bench scale test on the left there. And then once we proved in principle, working in hand in hand with the customer and with the ENC, then we decided that this would be a no-build solution and a low-cost solution to get us to work, to get the plant to where it needed to be. So by increasing the anoxic zone when we safely could, we would increase the retention time of the biology or the biological action in the anoxic zone to then further reduce the nitrate levels to where we needed to be. So that was the principle of the approach, and that's what we built into the system. So this was actually a customized system, but is now, we've done it so many times and we've put it onto our standard platform that this is available as an off-the-shelf solution now. So what you can see here is these red squares here is basically zone 1 of each lane, 1, 2, and 3. And what the controller is doing is to say, are my loading conditions onto the plant low enough that I can sacrifice 1 or 2 or 3 of the first zones or the first zone of each lane. So by constantly asking yourself whether you can do that, you then allow yourself in lower load conditions to safely sacrifice that volume. And it should be noted, this was a really highly loaded plant, but even highly loaded plants in the evening, the load drops away completely, and almost every single plant that I can think of will have a period within 24 hours that you can safely introduce an extended, or you can extend or introduce a swing zone to get all the oxygen benefits out of the nitrate and the alkalinity benefits. Here was specifically around total nitrogen, but the value, I mean, to release nitrate into the environment just seems crazy when there's so much alkalinity value in that nitrate and so much oxygen value in that nitrate. So for that reason, that's why we've introduced this as an option into our control suite. So yeah. So that was just a very quick story. So what I wanted to do, just wrap up. We've been using model-based systems. We've got a lot of confidence and experience of using those. So we've been doing that for over 10 years. There's so much benefit in having a good denitrification phase in terms of, extending the selector zone, improving the settlement, alkalinity recover, oxygen credits, and in this case, we avoided methanol addition, which was a huge relief to the end user as well, because very few people enjoy having methanol on the site. It intensifies the treatment available, and not only does it maximize the capacity of nitrification, it also minimizes your energy footprint as well, because you're squeezing all the value out of the nitrate when it's safe to do so. So and again, going back to Leiv's point, we've got visualization on this as well. So the fact that the operator can come in the morning, he knows exactly what his nitrate levels are, he knows exactly what his ammonia levels are, he knows the components, he knows how well his denitrification zone is working, he knows how well his nitrification zone is working, he knows how many nitrifiers he's got in his activated sludge plant. The skill level that is available, or the upskilling of the operator and the knowledge that an engaged operator can get from these systems when they realize it's not trying to take their job away and it's actually just a tool to help them do their job better. That's one of my main joys of commissioning is to see that light coming on with the operator when it's like,
thank you very much for that, Stuart.
This is why I run the plant this way.
This is probably the best time to ask the question from Leiv Rieger earlier. How do those operators react? Are there a group of operators that go, no, don't understand this, don't want to understand this?
Swing zone, so happy to answer any questions.
This is all just witchcraft.
If you visit a solution on an operator, then you're going to get resistance. And I think one of our learnings is it's so important to include operational staff right from the very beginning, and that's what we do, because essentially, you know, they're the guys who know which signals are telling lies, or unreliable, I should say, or which signal, you know, or the workarounds that they've done that aren't on any PNIDs. Or so by listening to the operational staff and by explaining before the system is anywhere near them, you explain what you're trying to achieve and why you are trying to achieve it. And you know, I've been sat in lots of rooms with operational staff shouting at me, "This is no, this won't work," and that's great, because you want them to say that as you're presenting the information, and then you can go into the deeper background information to then satisfy them. Because if you take them with you from the start, then the engagement and the likelihood of them adopting that system is so much higher. I mean, I know one of our systems, we had one of our chief designers visit the site, and the operator was gladly explaining how the system worked to the person who designed it. But he was so engaged with the system, it made his life so much easier.
We'll do all the other questions at the end.
When you
incorporate to calibrate, validate the ASM1 model for each application plant, plant?
That makes such a big difference in terms of system adoption. Well, every system that we provide comes with commissioning already. So we've got RTC specialists all across Europe, all across America, Australia, who are well versed in understanding how to optimize that. And because we've got that validated feedback signal, we know, not only do we know, or that gives you another piece of information, because you can tell how much the feedback element is weighting the DO set points. So just by understanding how much influence that feedback controller is, that gives you a level of calibration that is very difficult without both measurements. So yeah, I think we're at a point where we know which values we need to change quite quickly. So this is why it really is kind of an off-the-shelf product.
Thank you, Stuart, for a fascinating presentation. Our next speaker is Mikkel Dooley, who's the Managing Director of Strathkelvin Instruments, and he's going to talk to us about advanced real-time control of the activated sludge process using hour, or the oxygen utilisation rate. It's an important thing that's been around for many years but never really taken advantage of. Take it away, Mikkel.
Okay, thank you very much. Thank you for the opportunity to speak to everybody today. What I'm going to talk about today are our ASPCON range of products, the ASPTOX, the AXMON, and the ASSPI. So the TOX is for toxicity assessment, the MON is for compliance tracking in the outlet, and the SVI is obviously an SVI measurement device, which is part of the ASPCON suite. So if we look at activated sludge at its most basic level, if we can measure the oxygen uptake rate or the oxygen consumption in the plant, then we've got a really good measure for what's going on in the system. And this has been well understood for many, many years since the activated sludge process was around, but it's been difficult to do. So the oxygen supplied has three main uses. Obviously, there's the oxygen consumed for the biodegradation of the influent contaminants. That's the whole reason why we want to supply oxygen, have a treatment plant in the first place. There is also oxygen used to increase the dissolved oxygen levels in the plant itself, and that may or may not be used for biodegradation at a later time. Excuse me. So that increased dissolved oxygen level may make its way through to the final settlement tank, or as we've heard in the last talk, it may actually recirculate around with the RAS streams and actually have negative impacts on your anoxic zone. However, for most treatment plants, the majority of oxygen compressed and supplied by the air blowers is actually lost to the atmosphere, and this is the inefficiency in the process. So this can be a significant cost, when, especially if we consider that aeration cost of 30 to 70% of the energy cost for the whole plant. So just looking at some of the chemistry that goes on, we consume 1 kilogram of oxygen gone into solution per kilogram of BOD removed, and we consume 4.6 kilograms of oxygen per kilogram of ammoniacal nitrogen removed. So basically what's that saying to us is if we can measure the amount of oxygen that's being consumed, we then know the amount of load that's being treated. And once the oxygen demand has returned back to the endogenous or the starving background stage, then we know that the treatment is finished. There will be no more biodegradation taking place. So that's a very, very defined measurement that we can use to control the plant. So as I said, the knowledge about oxygen uptake rate and what it can do for us has been around for over 100 years. So initially we can look at the load that remains to be treated. So if we measure that at the outlet to the final settlement tanks, we can get immediate feedback. Is the plant compliant from a BOD removal and from an ammonia N removal point of view? We can also use it very quickly to look at a direct toxicity assessment on the activated sludge in the plant. And this is one of the critical parts and benefits of measuring OUR in the treatment works itself, is that if you measure on your acclimatized sludge, you will quite often get a non-toxic measurement or result, whereas if you use bacteria from other sources, from other treatment works or cultured bacteria, you may or may not get that negative toxicity result. We can also use OUR to look at the overall bacterial health. So are they readily available to biodegrade what's coming in? How many of them are nitrifiers? What's the oxygen uptake rate percentage for nitrification? We can look at short-term BOD measurements. And we can do fingerprinting of the incoming load to find out whether it's recalcitrant BOD or whether it's readily biodegradable, or how much fraction of each is there. So as we've all said, traditionally the OUR has been very difficult to measure, so it's not very widely used to control the activated sludge process. But we obviously think that we have a solution to that, and that's in our ASCON system. Sorry, I've gone forward too much. So the ASCON device sits in the activated sludge part of the treatment process. The measuring sensors are on the inlet, normally in the anoxic zone, but they can be anywhere in the aeration zone as well. We've got a local control panel which interfaces with the PLC and the HMI systems on the plant, and we've got an auto calibration unit working here. So what I'd like to do just now is play the video, which actually shows a sample taken. Thank you for starting it, Oliver. So this is our ASPTOX system. This measures toxicity at the influent of the plant. So basically the core and the shell drop down into the mixed liquors, and the sample flows in through the inlet holes in the sample chamber, which is then stirred and aerated. Because we have our own aeration device, we can put this into the anoxic zone. We then, so I'm now switching to a view where we're actually looking at the output of the dissolved oxygen measurements from the internal sample chamber on the ASCON. So the initial sample has been taken, the sensor was in the air, it's now down into the anoxic zone, so we can see the dissolved oxygen dropping to 0. We now inject the synthetic feed, normally an OECD 209 synthetic feed, into the chamber. That will maximize the respiration rate that's available. We aerate the sample. We're showing it obviously in a very much speeded up video here to a target DO set point of around about 3. We then allow the sample to settle to allow the air bubbles to disperse. And what you're seeing on the right hand side now is the actual oxygen uptake rate by the bacteria, because we're essentially got a DO probe in a sealed chamber. If there is no toxicity, the uptake rate of the oxygen should be to a maximum. And if there is any toxicity, then that oxygen uptake rate will reduce, and you can directly correlate the toxicity of the sample to that reduction in oxygen uptake rate. So if we don't inject in the synthetic feed, then we have an OUR or an actual current load coming into the plant. If we do inject in the synthetic feed, then we've got a toxicity result. So why do we like oxygen uptake rate? Well, it's been around for a very long time. There are lots of applications. So we can do toxicity, we can do loading, we can use it for plant control. It's also very accurate measurement. It's very easy to calibrate because it's based on dissolved oxygen calibration. And our systems are fully self-cleaning and self-calibrating. So basically we can grab a sample of the activated sludge and allow it to remove the oxygen in the system, which gives us a 0 oxygen point. And then we can take the sensor up into the air automatically, and that gives us a high oxygen point. And that's all you need for a dissolved oxygen probe calibration. What we really like about it is the amount of other measurements that it can do. So we can do loading, but we can also do toxicity. And this is interesting, I think, for all of our technology adoption rates and looking at all of the speakers coming in here, trying to find where we are on this curve. It's just a little bit of fun really looking at how long it took for certain technological advances to be adopted worldwide. And this is based on 25% of the US population. So you can see that initially electricity and the telephone took many, many years to be adopted worldwide, whereas the smartphone only took about 5 years for that adoption to run through. So we're always asking ourselves, where are we in terms of these new technology adoptions? Normally within the wastewater industry, we're looking at 10 to 12 years for significant adoption of new technologies. So again, to recap how the OUR is done, and then we'll go on to talk about some samples. So the ASCON system takes the sample, we aerate the dissolved oxygen to the target set point, and then we allow the bacteria to respire away that available dissolved oxygen, and then we calculate the respiration rate from the slope of the graph. So if we look at the ASCON system itself, the ASCON system itself can measure up to 20 key variables. Obviously, the ASTOX has got a significantly reduced number of variables, as does the ASPMON. The yellow highlighted ones are all measured by the oxygen uptake rate test, or derived from the oxygen uptake rate test. So we can see that there's a lot of information that becomes available once we can do this very simple test. The ASCON systems can also measure the settlement of the activated sludge and therefore calculate an SVI from the MLSS measurement that we've already measured from that system. And then we clearly have the other sensors such as dissolved oxygen, ammonia, temperature, pH available to the operator. So I'm going to go on and talk about some examples, but in summary, and I think we've all been very clear about giving the operators visibility on their treatment processes and what's exactly going on. There are many unknowns in the wastewater treatment plant. There are many things the operator does not have immediate feedback on, and quite a lot of these measurements are historically based. So for example, a BOD test can take up to 5 days to come through. So questions that we can be asked and are often asked in our consultancy work is, will the influent affect the treatment process? Is the plant compliant right now? How can we measure that? And what are the most efficient set points for dissolved oxygen for the MLSS? So we talked about sludge retention time control before, for the blower pressure. And OUR can go a long way towards giving you the answer to all of these questions. So this is actually the plant where we did a lot of development work for the ASCON systems. It was doubled in size. We designed an increase of throughput as we were developing the ASCON system here. It's on a landfill leachate system. Sorry, just trying to click this forward. So when we look at this plant, there are many immediate questions. The first question would be, is the plant in compliance? We can see very heavy foam. You can actually see in all the steel work and on the ASCON system itself, a lot of bacteria are being carried out of the treatment process on the foam. So we really don't know until we start to measure it, is it in compliance? And I certainly wouldn't like to be guessing that on a plant like this. Looking at the foam, is the influent toxic? Has that caused the foaming? Have there been any other issues created by that coming forward? And without an OUR measurement, how could we actually measure for these results? So give you some of the results for this particular plant. The OUR on the plant is actually 20 milligrams per litre. This ASCON system is located near the outlet, and we know that the endogenous rate is between 10 and 20. So from this plant's point of view, we're happy that this plant is actually, from a BOD loading and an ammonia loading point of view, it's in compliance. The mixed liquor was 3,200, again measured by the ASCON system. We've asked the operators to run this plant between 3,000 and 3,500, so that's spot on. We're happy with that. And the actual measurement of toxicity was no toxicity coming in the influent. Just to put you out of your misery, the foaming is actually caused by high levels of surfactant coming in the influent streams. So that foaming level is quite typical of the waste that would come down to this treatment plant. The ammonium in the outlet was measuring 0.2 milligrams per litre, so that was a further back up to the OUR measurement saying that there was, you know, the plant is in compliance at 20 milligrams per litre per hour and with an ammonium level of 0.2. The ammonium at the inlet to this plant is normally around about 2,500 because it's a leachate treatment plant, and the discharge consent is 8 milligrams per litre. And then just some of the other quick measurements that we could take with the ASCON system. Temperature is 35 degrees C, the pH is 6.8, settlement was 78 degrees, 78%, and the SVI is 69. Temperature is an interesting one here because that was actually how we managed to get this plant into compliance from when we first started, because the plant was running at around about 10 degrees C, which obviously for nitrification means that you have nearly no nitrification activity. However, this plant, so we've got the same plant here, did suffer from an upset condition on the 1st of January 2018. What you can see here is the yellow line is the OUR trace in the outlet. So generally it had been running between 10 and 20, around about the endogenous level, depending on the MLSS concentration. But we can see here at 310 on the 1st of the 1st 18, the OUR shot up in the outlet. Very, very high. So we went from an average of, let's say, 20 to an average of about 94, 95. And it stayed high for 36 hours before it dropped back down again. Because we were able to pinpoint exactly when the event occurred, the plant were able to go and find the source, which was an upstream construction site. And we were also able to back charge the additional aeration cost to that provider. Luckily, because we were in control of the plant through the ASCON system, we had recycle systems that we could actually send this back around to the front of the plant. This plant doesn't have to discharge at all time. It's got a lot of buffering capacity. So we were able to avoid an off-site discharge consent failure in this case. Just to complete the loop here, the dissolved oxygen also crashed when the OUR came in, which gave us confidence that everything was reading correctly. The ammonia, however, stayed very low at about 0.3 milligrams per litre, so we could tell straight away that this OUR was mainly made up from biological oxygen demand. Again, we often and almost in every consultancy process will be asked, can we treat this? Is it toxic? Can we push this through the treatment plant rather than having to use more expensive disposal options to incineration or landfill? So we got asked the question about this dye stuff going down to a pulp and paper mill. Is this toxic? This is some very heavy sludges from a refinery treatment processes in Europe. Again, is this particular sludge or influent to the plant toxic? Luckily, in both these cases, our measurements indicated that, while not ideal, the influents were non-toxic to the biodegradation process, so we could process them as we wished. But this is a site where we do pick up toxicity coming through. So we can see a very, very quick drop-off in oxygen uptake rate and performance when a toxic influent comes into the system. So we get an immediate feedback, an immediate reaction about the corrective action that we need to take. Again, looking at this particular treatment plant, we're asking the question, this is again near the outlet, is this plant in compliance? How would we measure it? How would we know? How would we be certain about the action of this plant? And we can see here that the plant is indeed in compliance, and the compliance has improved when we've implemented the RTC system based on feed forward and feedback, OUR and ammonia, so 4 measurements in each area. At the same time, we got significant energy reductions on that plant. So to recap, oxygen uptake rate, what can it tell you? So it can tell you the remaining load to be treated. If that's in the influent, it tells you the full load that's to be treated, so you know exactly how much air you have to supply into the system. It can tell you the required dissolved oxygen set points, which I've not gone through in this presentation, but I'm happy to take that in questions afterwards about how we calculate that. We can look at BOD levels. If our OUR has returned to the endogenous stage, we know that the BOD levels will be within consent. We can look at the percentage nitrification rate in the bacterial mixture. We can do bacterial health, which is an ongoing test that we can run on a daily basis. And in particular, we can look at toxicity of the influence to the bacterial sources in the plant. Again, this is a somebody mentioned storm surges before. When you are running plants in energy optimization modes, there is always a fear from the operators that if they get a sudden surge coming through the plant, will the RTC system be able to react quickly to it? On this plant, we have both feed forward and feedback control. And again, we detected the surge coming through in the influent in plenty of time to catch it, turn around the load and treat it before the outlet ammonia got more than 2 milligrams per litre against a consent of 15. So once the load was away from the treatment process, then we could return to energy optimization. So we look at energy optimization states. We've got 3 states where quite often the treatment works will be within compliance almost at the inlet for certain portions of the day, so we just need to do minimum treatment. We need to mix the samples, provide enough air for that to happen, the mixed liquor in the system. Other than that, we really don't need to do a whole lot of treatment, so we can go into deep energy saving mode, but we need to be ready at all times to react very quickly to influent loading coming in. And on this particular plant, we were achieving an 18% total site energy reduction by implementing OUR and ammonia feed forward and feedback control on the actual plant itself. This is the Cookstown plant in Northern Ireland Water. This was one of our first implementation projects completed, and we can see here that we got a 50% reduction in total site energy consumption, plus an increase in hydraulic capacity, as well as improved compliance data on that site.
So thank you, Michael. We are
so I'm now ready to take questions if anybody does have them. We have got some more slides at the end just to show some of the other options.
Time for a fuller discussion at the end with pretty much everyone involved. Thank you very much for that, Michael. I know OUR and respirometry have been around for years. Why do you not think that they have been particularly taken up as much as they should be?
I think there have been several efforts to make a reliable respirometer in the past, fairly well known back from the 70s, 80s and 90s. I think the difficulty has been the calibration of the dissolved oxygen sensors. There has been significant improvement in dissolved oxygen sensors, as well as in the cleaning and auto calibration of the systems. I think it's probably been an issue that because the instrumentation hasn't been available to do it, it hasn't really been taught in colleges, in universities. It's not really well understood by the operators. It's not really understood by the process scientists who are coming through the education systems. But we're hoping that now that we've got a reliable instrument that is easy to calibrate, that gives us the reliable measures and has all the software back up to run these tests, that it will become more widespread in its use.
Our next speaker is Mikkel Holmen Andersen, who's the Chief Technical Officer at Unisense. Mikkel's going to talk to us about nitrous oxide measurement and the control of nitrous oxide in the activated sludge process, and how by its use we can actually drastically improve the impact of the activated sludge plant on the environment.
Okay, thank you. So thank you for inviting me. So what we have developed is a nitrous oxide sensor. It's actually been on the market for more than 5 years now, but I'll go through some of the background and also the use of this sensor in process control, in particular in terms of carbon footprint management. So just a little bit of background on Unisense. We are a small company in Denmark, and primarily we sell equipment for basic research, microbiologists that are using our sensors, microsensors. But also have 2 sensors, the nitrous oxide sensor and also the sulfilogger sensor that measures hydrogen sulfide in the sewer system. That is part of our our portfolio of products. So nitrous oxide is actually one of the wastewater treatment challenges that are left. So we can do energy optimizations and we can do very good control of the processes, but there are some uncontrolled problems still ahead of us. And one of these is the emission or the production of nitrous oxide as part of the process. And as you can see, nitrous oxide is part of the turnover of ammonium all the way to free nitrate or to free nitrogen, and it's actually formed both in the mainstream and in particular in the side stream. One of the side or backsides of energy optimization is often that when you start to squeeze and optimize the aeration, lower the oxygen set points to save energy, but also increasing loading as cities grow bigger, then nitrous oxide becomes more of a problem. And without a visualization of the problem in terms of a measurement and a graph, then it's really hard to do something about the problem. So what we also talk about is moving from energy neutrality. You may know that many of the wastewater treatment plants in Denmark are actually net energy positive, so they are producing more green energy than they use. So what we are working with now is climate neutrality, where we try to be neutral in terms of the CO2 footprint, where we incorporate also methane and nitrous oxide emissions. And that the unknown challenge has also been measured in scale, both in Denmark, the US, and also in the Netherlands. And for a water utility, the greenhouse gas footprint can be up to 90%. The part that is from nitrous oxide, and on average, it's around 50% of the total carbon footprint that comes from nitrous oxide. So the process sensor that we made is an electrochemical sensor that automatically measures in real time the nitrous oxide dissolved in the liquid. But more than that, we can also calculate the emission that is made to the atmosphere, as long as we know the aeration system and the aeration volume that goes through the process. So we can do real-time CO2 reporting, and finally, we can provide data for smart control, mitigation controls, where we can reduce from 30 up to 60% of the nitrous oxide. So it is the world's only direct nitrous oxide sensor. There are off-gas systems out there that have been used also in the UK for some time, but they are quite expensive and they require a lot of working hours to maintain. This is a standard process sensor compared to an GO sensor or nitrate or ammonium sensor. It needs to be calibrated every 2 months, and it integrates into any SCADA PLC system, and at a cost that is very close to the cost associated with other types of process measurements. And connection options are quite diverse, so it's easy to integrate. So is calibrations that can be done easily within 5 minutes, comparable to a pH calibration 2-point. So it's a proven technology. We've been working with this since 2011, and it takes maybe 10 to 12 years to implement the technology. So let's hope it's this year that it will catch on. It's hard to come up with a new measurement unless there is a regulation, especially when it comes to greenhouse gas emissions. But it's on its way, and there is a new regulation coming in Denmark. But there are a lot of know-how around nitrous oxide. There are more than 40,000 papers concerning wastewater treatment, and more than 1,000 of these are using one of our nitrous oxide sensors, whether it's research or the wastewater treatment plant type of sensor. And we have around 200 sensors in place running 24/7 today. One of the reasons why this is catching up now is actually that the carbon footprint from wastewater treatment plants is increasing as cities grow bigger, and we use more and more food around the world based on fertilized farming land. So the nitrogen ends up in our wastewater treatment plants. And last year in May, IPCC, that is controlling or doing all the founding research for national emission calculations, they changed their emission factors from the one that they used in 2006 from 0.035% of the N that comes into the plant treated will end up as nitrous oxide, and by May 2019 it's now 1.6%, so a quite significant increase in terms of the carbon footprint. And this is the key number that is actually used by all countries to report into the UN system. So for the water utilities, it's starting to become more than just the 50% of the total carbon footprint. And the data behind a lot of this in the IPCC report is actually coming out of this chart here, where you can see that most of the wastewater treatment plants, at least in Europe that we know, are with a load of less than 3 tons of nitrogen per day. And if you look at the data there, then we really need more measurements. So hence the sensor that we provide will help to monitor and to provide more input into the problem, but also to alleviate the problem by enabling process controllers to engineer new process control systems. So just in terms of the emission calculation, so this is one of the questions that we always get, whether we can reliable from a liquid measurement calculate the emission that comes out of the system. And here it's actually shown in a Swedish wastewater treatment plant that it's fully covered, it's underground, and there's one big chimney that comes out from the wastewater treatment plant. And in that plant there's an 80,000 cubic meter aeration zone that we have a single sensor sitting in the middle of this, and we calculate the emission based on the liquid measurement of nitrous oxide and then the airflow that we measure that goes into that aeration zone. Then in the chimney we measure with an off-gas instrument with green. We measure the nitrous oxide concentration in the off-gas, and you can see how well this compares. And this generally complies within plus minus 10% of the off-gas measurement when we do the calculation. So we get a pretty accurate emission calculation based on a liquid sensor measurement, and the references are shown up here in the slide. So how many sensors to apply to actually know what is going on? Well, this is a raceway fully mixed, where we have had 4 sensors in the same raceway, an activated sludge plant running an alternating system. So unlike some of the examples you've seen before, where you have swing zones, here it's actually easier to control whether we have a longer or shorter aeration time or denitrification time by switching on and off the air in the full tank, a common process here in Denmark. But what you can see is that the nitrous oxide is actually measured and quite comparable in the four position. So rarely more than a few sensors is needed for a single plant to get started with the nitrous oxide measurements. This is actually from Severn Trent. Peter Vale and colleagues have measured the nitrous oxide in a plug flow system, and here you can see the variation of nitrous oxide as a function of DO set point, but also as a function of how much carbon is left for efficient denitrification or removal of nitrous oxide, which is part of the denitrification. So basically measuring here is needed to understand what the emission and the impact of, for example, energy optimization will be on the climate. Another thing that is really important is, so I think the text comes up weird here in the original, it looks different. But here it's actually a full year monitoring of 4 parallel tanks at Biofos, one of the largest wastewater treatment plants in Denmark. And you can actually see the variation over the year, that it's really seasonal dependent. So during the spring and the summer month, we have high emissions of nitrous oxide, whereas during the winter time, it's less profound. this is not a general picture that we see. We do see during the winter time at plants where we are efficiently harvesting a lot of nitrous oxide, a lot of COD out for biogas, that we will have problems with efficient denitrification here, and that's because the endogenous hydrolysis of COD is very slow when the water gets colder. But the take home here is that you need to measure throughout the year to really understand how to do the process controls. You cannot measure for 14 days or even make a model of this and then get it to understand. The nitrous oxide models are really, really difficult to calibrate and rarely last or hold their calibration for long. Zooming in on an April month last year, you can see the daily average, and really nitrous oxide is just like the ammonium and the nitrates. They go up and down with rain and with load. And here you see the beginning of the spring and the increase in the nitrous oxide as we go along. With very little sensor drift, it needs only calibration every 2 months. But what is also importantly is that in this period here, 1.6% of the N that ran into the plant actually went up into the atmosphere as nitrous oxide. And if we look over the whole year, then we can actually see that 3 spring months are actually the main source of the total emission for that year. And for a whole year, the emission is around 2.6% of the N that came into the plant actually went up into the atmosphere as greenhouse gas emission. And doing a control, trying to tune that in November, December 18 wouldn't make any sense. It's actually in March, April, May that you need to work with the emission control on this particular plant. And the monitoring in terms of the online reporting, which is becoming more and more important in terms of sort of the third bottom line for utilities in terms of greenhouse gas bookkeeping. This is now an online feature that is running in real time and now made not on a key number that is really a guesstimate, but now measured in reality. In terms of control and emissions, so Unisense environment, we are not delivering emission controls. It's other companies that you have heard talks from today, but we provide the sensor and share all the know-how that we may have. But as you can see, if you only measure oxygen, then you will actually lack information of any of what is going on in terms of nitrous oxide. And measuring ammonia and measuring nitrates will give you some information, but really what we need to measure is the nitrite, which is sort of the cornerstone between the nitrification and the denitrification. And understanding the level of the nitrite is really important. And here the nitrous oxide sensor becomes really, really important because there's a close linkage between the nitrites and the nitrous oxide. And this is actually shown on this table here at the same plant as you saw before with the 4 sensors. Here you can see the purple, which is the nitrous oxide that is being formed as we convert ammonium to nitrates. Then the nitrous oxide comes up. If we dose some ethanol to enhance the denitrification, then we can get the nitrates to disappear. We don't measure a lot of nitrate, but nitrite is there, and we measure this in graph samples to be significant. Again, this is a plant that is highly optimized, running at DO around 0.5 to enable simultaneous nitrification denitrification. So if we enhance the denitrification, then we can actually lower the nitrous oxide quite significantly because then it's processed to free nitrogen. And just to prove this, over-aerating, as you heard before, doesn't help a lot in terms of turning over more ammonium, but what it generates is a lot of nitrate now, because now the nitrite is becoming to nitrate, so from NO2 to NO3, and then the nitrous oxide starts really to increase, and actually it maxes out in terms of our sensor sensitivity. So carbon control and ammonia control are really important. Another thing that's also important is actually sludge control, and having a higher mixed liquor concentration is quite important, because the level of ammonium turnover per bacteria is directly and proportionally linked to the specific production of nitrous oxide. So if you turn over more ammonium per gram of bacteria, then you also produce more nitrous oxide exponentially per gram of bacteria. So having a higher MLSS is really good for lowering the nitrous oxide, so less work per bacteria, and also a high turnover of ammonium, which is typically the place if you start to stress or you increase the load on a plant, then you will get higher nitrous oxide emissions. Load is exemplified here. So in the plant that you saw the year-long monitoring from before, there was a 25 days period where the load was lowered 50% in 2 of 4 lanes, and immediately you see that the nitrous oxide is reduced by 92%, but overall in the period about 33% of the reduced nitrogen treated was now not ending up in the atmosphere as nitrous oxide. So lower load is really important. So bigger plants comes with new problems in terms of greenhouse gas problems. Different processes give different signals or footprints of nitrous oxide. And just to show that what you have already shown seen by Hach and inCTRL solutions, stimulating simultaneous nitrification denitrification is one of the keys to lower the nitrous oxide footprint, which is shown at the last part of the blue graph here, where the DO set point is lowered all the way down to 0.2, 0.3, and you can see that the nitrous oxide is actually dropping down to the detection limit of our sensor. So just working with the controls and having nitrous oxide in there in the feedback loop will actually enable nitrous oxide mitigation quite easily, and actually give you a full insight into the denitrification. And you can play with the aeration strategy to save energy, but you immediately see that if you do an energy efficient process control, then nitrous oxide will be one of the backsides. So the green dots here is the emission in kilograms N per day. That is significantly increasing if you start to energy optimize. So when you do these ammonium controllers, then having nitrous oxide in there as well, if you do have a third bottom line or a greenhouse gas bookkeeping as part of your control goals, then this is key to have. Carbon management, for example, dosing methanol or just using what we use here in Denmark is internal fermented primary sludge as a carbon source. You can actually use this to enhance the denitrification so that you can lower the emission. In this case here, compared to the control, we have a 30% reduction just by controlling the amount of carbon available. And this is also shown in a case here in the US where they dose Micro C, which is a complex COD mixture. And here you can see a really beautiful correlation between nitrous oxide and then the stoichiometric need of carbon per N turnover. And that is actually around 3.5. And the moment that we hit that ratio in dosing of carbon, then the nitrous oxide completely disappears, because then we enable a full denitrification. So one way to use our sensor is actually to control COD dosage. Due to lack of time, I'll just skip this. It will be part of the slide deck, but Veolia is also working with reductions as well implemented in their control strategies. So in summary here, it is possible to do climate-friendly wastewater treatment with nitrous oxide sensors, and we can actually with easy control. So no building new wastewater treatment plants, but just controlling the process better with the new insight. You can actually reduce a lot of the impact from the wastewater treatment by input of a new sensor. And in Denmark, right now, it's already passed through Parliament in an agreement, but now needs to be implemented as a regulation in Denmark, is the obligatory monitoring of nitrous oxide, and then eventually also levels that you have to be below. So the final slide is really that real-time nitrous oxide measurements is possible, and you can do real-time CO2 equivalent bookkeeping in your SCADA or ERP systems. Well, maybe in this form here, most importantly, it's actually an extra tool to give you a lot more insight into your nitrification, but also and especially the denitrification and how well it works, so that you you have a much deeper insight into the process. So that's the last slide.
Lovely, thank you, Mikkel. A quick question from me: is it not a no-brainer now with a lot of the water companies, around the world driving towards net zero? Wouldn't a nitrous oxide sensor be an absolute no-brainer?
Well, in terms of you know, the climate act and in terms of the footprint, for sure it will be. The problem is the cost of the equipment for something that is not regulated. Where and how should they pass on the cost to the end users? So in Denmark, for example, it's so that if there's a regulation in place, then they one-to-one can put and push this cost to the end user. So it's more a political question than it's a process engineer question when it comes to implementation of the sensor.
Yeah. No,
so the utilities.
But I mean, I know there are a lot of utilities on this call who will be looking towards innovation to drive the agenda down to net zero, and this is an obvious innovation that almost from an environmental perspective is absolutely a must-do almost.
Yeah. The key here really is that you cannot guesstimate the emissions. You cannot use key numbers, just like you cannot estimate the amount of ammonia at the end of an aeration train without having a measurement somewhere. Key numbers will not work, and they will not be valid across several plants.
So thank you for that, Mikkel. We are running a bit behind schedule, so I will very quickly.
Thank you, Mikkel, for a fascinating discussion that should lead to nitrous oxide being adopted more widely. Last by no means least, we have Jordan Schmidt, who's an applications manager at Lumen Ultra, and he's going to talk to us about ATP and its use in activated sludge plant control, something that's never really been considered before, but is something well worth looking at. Take it away, Jordan.
Thank you very much, Oliver, and thanks for having me today. And big thanks goes out to my co-presenters as well. Really interesting presentation so far. Today I'll be presenting on ATP in activated sludge FM control. So as Oliver said, my name is Jordan Schmidt. I'm the product applications manager at Lumen Ultra Technologies. So what is ATP, or adenosine triphosphate? It's the active energy molecule in all living organisms. It's actually so a direct measurement of ATP, which can be done in approximately 5 minutes, is a direct measurement of all biological activity. And the reaction that's actually occurring that we're actually measuring is the same reaction that occurs in the tail of a firefly. So that's an ATP reaction. It's generating light. Similarly, we can harness that and measure the light output to measure quantity. So if we look at just kind of a general black box look at kind of what your MLSS is going to be comprised of, inorganic and organic kind of inert compounds, living biomass, dead biomass. It's comprised of a lot. Kind of harnessing in that a little bit closer as we move to kind of just the volatile suspended solids. We get rid of those inert organics, but there's still a lot of organic compounds that are inert, not contributing to treatment, and dead biomass as well, alongside the living. And then finally, there's the ATP, and in this case, it's cellular ATP, so it's intracellular. There's no extracellular component at this point, and this is just going to be the living biomass. The fraction of the CATP to the MLSS or MLVSS changes quite significantly from plant to plant and how the plant is operated. So there's not a set quantity of living biomass per MLSS. We've seen it range from less than 5% to greater than 75%, and there certainly is a sweet spot for each plant. So it ranges greatly. You can't necessarily just rely on a assumption of biological activity quantity or ratio of that MLSS or MLVSS. There's also a dissolved ATP component, so something that's showing kind of an indication of dead biomass or recently dead biomass. So whatever kind of the extracellular DATP, you can kind of look at recently lysed cells from acute toxicity and stuff like that. So it's not a direct measurement, but it is a direct measurement of what's recently been killed, and that shows those lysine agents are going to cause the cells to break open and dump out their intracellular components, and ATP is one of those. So in terms of the methodology, it's really measuring two different things, the total ATP and the dissolved ATP. The total ATP is comprised of both cellular and dissolved, so you can then back out the cellular concentration. So for the total, we're going to extract the ATP, which is the cellular. And then for both metrics, we're going to dilute out any interferences. So there's a lot of potential interferences in a wastewater matrix. We're going to dilute those out. We then react with a luminescent enzyme, which is luciferase. So that's our little firefly. That's the reaction that occurs in the tail and other bioluminescent organisms. And then we're going to measure the light output, and we're going to compare that back to a standard ATP concentration. And the units of that measurement are then going to be nanograms per milliliter. So it is a quantitative measure. Just a couple of kind of key process indicators. So again, we have our cellular ATP, that's in nanograms per liter, or nanograms per mil, however you prefer. This represents the amount of ATP contained within the living cells as a direct indication of total living biomass quantity. The active volatile suspended solids, or AVSS. So it's really just a unit conversion, and it's converting that CATP in nanograms per mil or liter into milligrams per liter. It's really just more of a bit of a switch because people have a hard time conceptualizing the nanogram unit, so we want to get it over to milligrams. And that would be more as carbon as opposed to just purely as ATP. The biomass stress index. So if we look at the relative ratio of dissolved ATP to total ATP, that's going to give that measure of potential stress level within the microbiological community. And then the active biomass ratio. So how much of that MLSS is living biomass? So we take our AVSS, or the ATP times 0.5, divided by the MLSS, and that gives the percentage of total suspended solids that are actually living. And that's going to range fairly greatly from site to site, and depending on how the sites are operated, and also looking at different types of industries, whether it's is it municipal, is it refinery, is it pulp and paper? They all kind of have a expected active biomass ratio. So kind of switching over to food to microorganism, or food to mass, F to M, however you want to refer to it as. It served as a widely used process control parameter for activated sludge. The objective here is really to balance the biomass quantity with the amount of biodegradable or oxidizable matter that's coming into the system. Traditionally, that food proportion of the F to M would be calculated using BOD or COD, with the microorganisms calculated as MLSS or MLVSS. These do have limitations, specifically analysis time. So, BOD, you're looking at 5 to 7 days, depending on how you're measuring it. MLSS might be overnight. That really restricts your ability to use it as a rapid process indicator and make real-time change. So there's also responsiveness. So just kind of looking at those two examples below, so an increase in food, I would expect an approximately equivalent increase in active biomass, but because that active biomass makes up such a small fraction of the solids, you're not going to see much of an increase there. So the F to M is not going to change as much. Now looking at a decrease in food, so again, an equivalent decrease in the active biomass, but there would likely be no immediate change in the MLSS or MLVSS, as a starved organism is still going to have the same mass as a actively growing one, but would have much less ATP. So the expected F to M model that we would be looking at here, there would be an optimal range with treatment performance decreasing as F to M increases, and there's a shift to endogenous decay, but also increases, also decreases as F to M increases as there's just a insufficient active biomass. So it's going to kind of go, a bit of a curve like that. So I'm going to kind of spend the rest of the time talking about a case study that we did. This was published last year in WE&T magazine, and it was using what we're calling true F to M at a refinery water resource recovery facility. So the treatment process was a conventional activated sludge facility with nitrification. It had dissolved air flotation on the upstream, multiple plug flow activated sludge bioreactors, and secondary clarification. For the food metric, we used a bit of an innovative technique here with the Suez Sievers Innovox dissolved organic carbon analyzer. They were a good partner of ours on this project, and they were a co-author on the magazine article as well. So this is, we really liked it. It's a rapid technique. It uses the supercritical water oxidation. So it's validated for a wastewater matrix. No concerns about fouling over time, stuff like that. Then the microorganism metric was using the luminal QG21W ATP, represented as active volatile suspended solids. So that's that unit conversion from nanograms to milligrams. And this is a rapid, it's designed for wastewater specifically, thus the W in the name. And it's just it's a complete measurement of biological activity. So for data collection, so we had 12 months of process data collected and analyzed. This included daily BOD, DOC, MLSS, CATP, along with a full suite of other parameters, including ammonia, nitrite, nitrate, conductivity, pH, and dissolved oxygen, and a whole bunch of other parameters. So looking at this figure, so we have biochemical oxygen demand removal as a function of the F to M ratio calculated using BOD and MLSS. So this is the traditional way of calculating F to M, or at least one of the traditional ways of calculating F to M. I know that there are multiples. We did knock off a couple of data points just from the scale, not from the model, that exceeded 0.8. And then the curve that was fit using the lowest regression, and it has a 95% confidence interval represented in the shaded band. So just a note on the lowest regression, so that's a local regression model. It's not drawn in, it's fit using our, I used our statistical software to fit the model in. So just a few kind of highlights. So, we had significant variance. The 95% confidence interval band was quite large. And then we also kind of had this, up, down, up, down, up, down. There was no real obvious range for the F to M. There was not really necessarily one kind of sweet spot that we'd want to be operating in to maximize BOD removal. Switching over to when we use what we call true F to M. So again, this case we have dissolved organic carbon removal on the y-axis, and then we regressed it as against the food to mass or food to microorganism calculated using DOC and ABSS or ATP. Again, we knocked off a couple of data points, but just from the scale, not from the model. And again, the curve was fit using the same model with the same lowest parameters, same span, everything like that. So here we had this very obvious kind of optimal range that was from about 0.5 to 0.9 kilograms of DOC per kilogram of ABSS per day. So the variation or the variance, the confidence interval was also a lot tighter within that data point. And there was just that nice flat line. There was not a kind of an up-down pattern. So I just kind of want to give a couple examples when we look through the data of, I'm going to throw it up a little bit goofy, but about kind of how this could be used in practice. So this is an example of where F2M was kind of failed to act upon. So the gray band is that optimal range, the 0.5 to 0.9. In the green line, we have F2M, and this is the true F2M, the DOC over ABSS. And then we have DOC removal in red. So we had this very extended period of suboptimal F2M. It ranged from kind of, let's say, start of June through kind of basically the end of June. It was almost an entire month long. That kind of also showed or also resulted in a reduction in baseline treatment performance. So we were up around 90% before, we dropped down to 70% before it finally recovered. And it was actually a bit of a coincidental F2M recovery associated with increase in DOC loading. So that kind of also resulted in that exact recovery of treatment performance as the F2M went back into that optimal range. So we're going to look at kind of the implementation in practice. This is kind of an example where the F2M optimal range was acted upon. So again, we have the F2M in green, the DOC removal in red, and the dry solids or MLSS concentration in blue. In terms of axes, the F2M and DOC removals on the primary axis, while we have total suspended solids, a mixed liquor suspended solids or dry solids concentration on the secondary axis. So things are going pretty well. Again, we have the gray bar representing the optimal range. F2M was tending to just kind of stay there. Treatment was going well, above 90% removal, which is what they're targeting. And then something happened. And I always try to think of this as, what's my insight? What am I getting from this information? And what am I going to do about it? So we had a suboptimal F2M detected. It was down around 0.3. The lower bound was 0.5. So the action that we're taking here is to decrease the recirculated sludge flow to rebalance that F2M. So you can see here in the blue line, the MLSS was starting to decrease over time. We were pushing that down. And then that resulted eventually in the F2M rebalancing, the ABSS rebalancing with the amount of food that was coming into the system, and the treatment performance recovered. Over the next few weeks, you can see the solids concentration had to be continually dropped down. This was due to a dramatic drop in the loading to the facility. But in general, they were able to. They had some issues with it bouncing in and out of the optimal zone, but they were able to kind of keep pushing it back up and recover their treatment performance. So just some implications for activated sludge process control. So in the current term, we have a rapid F2M method. It's minutes to complete. Action can be taken immediately. This isn't something that you're going to be waiting 5 to 7 days or even overnight to get a result so you can take action. It's a direct measurement, so it's going to support that site-to-site comparison. You're not accounting for differences in influent composition or sludge activity. We're hoping that because you're doing a direct measurement, and we need to kind of do a little bit more studies on this to confirm, but you're going to be able to support that site-to-site measurement and potentially consistent optimal ranges. in the future. So DOC, it can be measured online currently. And then we've also launched an online ATP analyzer, Bug Count Online, that's currently being adapted for a wastewater matrix. Automation, so using the online features of F2M, maybe eventually we'll be able to automatically control a plant, whether that's with kind of give feedback to an operator to make the change, or eventually we'll be comfortable to the point where maybe direct changes can be made. Then I'm going to add in a third one there is, how does the F2M influence the kind of other process parameters, whether that's, SVI, whether it's, nitrification. So we've done a few studies there. We will have a presentation at WEFTEC coming up this year, or WEFTEC Connect, I should say. And then, can this F2M parameter potentially be used as a leading indicator of problems kind of downstream of that carbon removal, such as nitrification? So I kind of zipped through there quick, as I know we're short on time, and I'm looking forward to the conversation. So I just want to thank everyone for joining, my co-author or my co-presenters. And,
so thank you very much, Jordan. It's been an absolute pleasure, and thank you to you and all of our speakers. I will now move us towards the sort of discussion element. If I get all of the speakers to turn their cameras on, and I will turn my camera on, and we will move towards a sort of a chat. So to everyone, certainly do answer some questions. Thank you, Laurie. I can see you're typing already. We've heard some great things today. We really have. Do we control enough on ASP? I mean, realistically, it's a largest big hairy process in the water industry, especially on the larger works. There are elements of DO control, there are elements of ammonia control. Sludge age control, certainly when I was working with water companies in that area, it was, even basic sludge age control was over £1 million in savings every year. Why is not every single large ASP plant in the world got some sort of advanced control system? Or is that me being naive?
I can try to give an answer. So one thing you have to keep in mind that has not been discussed, of course, we are all trying to promote our technologies here, is if you properly control, you drive the plant or the system to its limits. So you're increasing the risk. So who's taking that risk and how do you mitigate that, right? So our focus is actually a lot on data quality to make sure that you have the right inputs. If you don't, if that system fails, you violate your permit and then the operators are in trouble, right? So you cannot just say we throw advanced control at a plant and then everything is fine, right? So you have to organize that everything actually works. Another one not really discussed is cost of operating these systems, right? So my rule of thumb is 1 to 2 hours per sensor per week. And that's a realistic number we actually monitor, right? So how much time goes into that. And there's always that odd moment, and it's not the fault of the suppliers, right? But it takes time, right? And if you include that in the cost-benefit analysis, unfortunately for smaller plants, there is no benefit, right? Because maintaining the sensors, we saw that example from Hach, right? 17 sensors I counted, right? So multiply that, right, by 1 to 2 or by 2, and then for 52 weeks, and then whatever an operator hour cost, right? $100, whatever you have, do that math. Right? So there is no way you make that beneficial, right? So you have to be very careful how you set that up, mitigate risk. You have to automate, and I think Hach does a wonderful job doing that. But so it's a lot of automation, packaging it, so that it becomes cheaper. But 17 sensors for that plant, no way that there's any benefit coming out. Purely energy cost, right? So you have additional benefits in terms of understanding the plant better. You have side effects, but it's quite expensive.
Is it? I mean, I suppose it does depend upon the sensor and depends how experienced the operator is, so that there is training in there as well. Because I remember dealing with the works with one of the water companies, had 40 on a single ASP. They had 40 DO sensors, and one operator could string that job out for basically a week. Another operator would come along and do the same job in 20 minutes. So that's a very simple DO monitor. If it's an ammonia monitor, well, pretty much. If it's an ammonia monitor, well, pretty much most ammonia monitors of the ammonia monitors on the market, they're pretty good, and they don't need vast amounts of maintenance. But I suppose the education as well. Yeah.
I think that's a good point, Oliver, and towards the different types of operators. And I think that's something that's kind of maybe will eventually drive this all forward. Is I'm not sure what the situation is like in the UK, but and in Europe in general, but the aging operators, the aging workforce that runs these facilities, eventually there's going to have to be something that comes up in the rear, and it doesn't seem to be young operators.
Yeah, so I think it's education as well. I was speaking to one of the UK water companies yesterday, and they were going, well, we have trouble to encourage somebody into instrumentation and automation, and we're seriously trying to change it in the industry. That's when I let them know about the instrumentation apprentice competition I run, because it's not having those apprentices. They can go into electrical, they can go into instrumentation. Of course, most of them go into electrical. But we have got some quite interesting questions. One from Laurie Reynolds. 5 speakers clearly understand their sensors, but nobody is able to support all the technologies applied on a plant. I think we need to be discussing how a service model can be applied to this problem. And maybe that is, I think Laurie's got a valid point. We're seeing data as a service. I'm certainly aware of one maintenance company that services at least 4 or 5 of the UK water and sewage companies just in maintaining ammonia monitors and DO monitors. So in some ways that already exists. I think some of the companies will, when they look at the cost of that, will turn around and breathe in stiffly, but I suppose that's maybe the cost. And when it comes to the technologies that are being applied at the moment and the intensive treatment technologies, I'm mainly thinking about the ASP variations, where they're very instrument heavy. I think it's going to become more and more important. In short, Laurie, do we see young operators coming through the system? Generally, no. Question from Howard Thomas of Thames Water. Leiv, what is the cost benefit of measuring mass airflow into each zone and controlling via mass airflow as opposed to a direct DO control of valve position?
Yeah, so there are a couple of reasons doing that. One is that you linearize the valve in basically having an additional control loop in there. The other one is that if you are not measuring airflow, you cannot put bounds in, right? And mainly if you use, again, ceramic diffusers, and if you go lower than a certain limit, then you may destroy them. And airflow for mixing, same thing. There is a certain limit you need to maintain. Little anecdote, I once, so as a PhD student, I questioned everything, and I actually turned it down too much, and I thought airflow for mixing limits is just for somebody not daring enough. They had concrete fouling and had to repaint the whole tank after. So it's important. I learned my lesson.
Michael.
Hi, Oliver. Just coming back to the service and maintenance part of the equation. I think it's a very good question, and something that when you look at the amount of new technologies that are coming along, it's they're very, very different. They all have incredible applications, and we need to look at you know, where we apply them and how we apply them. But one of the biggest benefits coming along is remote access, to allow manufacturers and the people who understand the instrumentation best to be able to remotely dial in to instruments and to actually carry out a lot of the maintenance online. I would say with our instrumentation, we're looking at maybe about 90% of the activities can be carried out remotely and online. I know there's lots of issues with trying to get that access and lots of concerns about cybersecurity, etc. And then we're really looking at the lower level of task activity needs to be done at the plant.
I'll try and hold Stuart back here. Of course, Hach have got the Claros system, which is definitely aimed around that instrument health and doing a lot online. I'm personally a big fan of it. Other companies, Endress, have got their system, which again is very good. I know that they can dial in remotely, but as you said, cybersecurity is an issue. And actually, that's an agnostic platform that will deal with not just Endress sensors, but everyone's sensors. But it's that yes, there's always going to be a certain amount to do at the plant. For one thing, cleaning to a certain extent. Yeah, and there's a lot of, on the instrument health angle, there's a lot to be doing. Stuart put his hand up there. So Stuart.
Yeah, I think one of the points to make as well is we're very good at identifying the cost of maintenance, and maybe as an industry, not so good at understanding the cost avoidance of what good control can bring you. So I think when people understand the actual energy benefits that come with that, then, and it's difficult when you've got a siloed organization where the maintenance budget is a different budget to the operational budget, so there may not always be the same drivers to maintain that budget and things like that. So there's maybe some harmonization across our industry that would make the justification and the value that's being presented by the more advanced control systems. I think that's our responsibility to help paint that picture as well, I think.
I just before Mikkel dives in, I'll say, yeah, I mean, when I was in a water company, it was a case of the avoidance. A category 3 pollution incident, for example, had a very defined cost to it. The avoidance of that category 3 pollution incident, as an example, you didn't really know. So I suppose there's that risk and that risk point of view, and the cost of avoidance needs to come a lot further in. Mikkel, you had something. I think you're on mute, Mikkel, because I can't hear you. Yes, can, yeah.
Can you hear me? Yeah. Okay. So a general comment, I think as an industry, also as solution providers or component providers, we need to make it interesting to work in the water business for the young people. And one of the ways to do this is by implementing active controls, because that has a taste of technology, IoT, and so forth. And the cost and and it costs to have a good environment. And the way that it works in Denmark is actually that we have a tax on the effluent. So if you pollute more, if you go lower than your permit, you still save money. So that is the real driver for implementing advanced controls. This is why we have full BNR on all our plants, because otherwise they will have to pay. And in the end, it's the end users that are driving this. And that brings me back to my last comment is, it's really through regulation that we advanced the environment. It's not by the goodwill of a utility. They need a way to allow for costs to be distributed to the end users. And that means that we need to be able to provide, total cost of ownership and these type of calculations, including the savings on effluent taxes and so forth, by implementing our technologies.
Just one add on here. So in the US, never call it a tax, call it a fee. It helps a lot.
I think that is key, because when you look at some of the, should we say, the more advanced countries in the wastewater industry, there's probably a correlation between an effluent charge, should we say. So for those of you who aren't aware, there are some countries that, yes, you have your allowed discharge, but every kilogram or every ton over that amount, you get charged for. So the cost-benefit analysis suddenly becomes a lot easier if you know that for every kilogram of BOD, every kilogram of ammonia, arguably every kilogram of nitrous oxide, you're going to get charged more for. And
But the case in Denmark now is that we are world champions in making energy efficient and to the limit purifications. But to move that further, then we need a new stricter regulation. So every utility will find the optimum always.
I spoke to a Danish person who worked for a Danish water company about a year ago now, and the person turned around and said, "Yeah, we actually haven't had an environmental permit for about 15 years now, because there's been some mix-up with the local council, etc., etc. But we know what we should be working towards, so we just do it." And I think that's it's something I mentioned in the chat, that the environmental responsibility of the Danish in particular is world-beating. It really is, and you see so many innovations and so many things around this adopted in Denmark because of that environmental responsibility. Mikkel, you might be able to tell me.
I think what adds. Yeah, so I think what adds to that is the Danish model is that you have these roundtable discussions, right? So you bring all the stakeholders together, and that. So it's not just legislation. I think it's really a model for the world, that you bring all the stakeholders together and you discuss that together and discuss how to improve. And I think that's the recipe for success.
That was actually my comment, is that for every technology to be implemented, you can actually negotiate a window where you can trial it out, so that it's okay that you are above permit for a period, and you can avoid the fee as well. But that's the only way that we gain new know-how. Maybe it will survive and become BioP, which is also run at most plants in.
Just to answer your point, Laurie, couldn't agree more. It is an argument for advanced control and net zero, and I think that was my point with Mikkel. The nitrous oxide sensor just seems a no-brainer, and realistically, when you look at it compared to other monitors, then it's not expensive at all. But yes, I think the whole thing should be driving it. And I think the water companies are doing that, to be honest. So yeah, it's absolutely. And in some ways, I think we are seeing some companies going towards that. Equally, Laurie, on your interoperability and open data models. Yes, they are, and that's why I chatted to you, was it earlier this week or late last week, about the IWA interoperability workshop that's coming up. And I think more and more that message is starting to get through. So unless there's any other questions, I saw there's one potentially for you, Mikkel, by Rob Stevens. Directly controlled blower technologies, but adoption innovation is not joined up. Approaches can measure BOD in real time. I suppose you can do a similar sort of thing with OUR. You're on mute, Mikkel.
Thank you. Yeah, absolutely. The BOD measurements and the OUR measurements, they each have their place. Certainly there's capability to control any type of aeration system, whether it's a blower, an air mixer, a surface agitator, whatever type of aeration you have there. And it's interesting to see the amount of technologies that we have coming forward. And interesting to look at what the treatment plant of the future will look like. It would be nice to get a model that maybe has the ideal setup and look at the benchmark that plant could achieve in terms of kilowatt hours per kilogram of BOD equivalent, so including ammonia removed. And it can drive the regulatory scenario as much as the operating scenario.
Yeah, if I remember back 10 years ago now, and I was shocked to see it was 10 years ago, the Dutch, through STOA, produced the wastewater treatment works of 2030, very much talking about the factory approach. Is it time to refresh that, do we think? Open question.
Well, I mean, from my point of view, I think it's looking at the standard. I think the world has changed so dramatically in terms of the technologies that are available. I think also in terms of the understanding the processes that we need to go through with the water companies, you know, having a very specific process of assessing the plant, setting the baselines, working through it, looking at the nitrous oxide emissions, looking at the overall environmental balance of what we're doing, and the understanding of that has grown. And I think it's already been mentioned in the questions, where we're looking at not only the operator skill sets, but also the operator availability as we go forward. We're very much changing the type of job. We're looking for highly competent, highly technically skilled people, able to run advanced PLC-based control systems and take significant decisions. And yet at the same time, we're also asking them to clean screens and to look at maybe some of the less savoury aspects of the plant. So there's a real dilemma in terms of how we set up the plant and who we're going to get to run them and who we're going to get to maintain them and service them going forward.
And to be honest, I think that comes back to the Danish system, because, and correct me if I'm wrong, Mikkel, but the Danish were facing this issue 25 odd years ago, realised it at the time, and took the bull by the horns and dealt with it, and just see where the Danish are now.
We had massive death in the seabed in the inner fjords in Denmark in the early 70s. So that's when they started to implement.
Yeah, I mean, there obviously seems something there around advanced controls. We've got a whole digital transformation piece at the minute, as most people will know. We've got some fantastic companies here. Is it something we need to take on? And is it something we need to find a home, get the experts around, and produce a wastewater treatment works to say 2050? Again, if you look,
certainly be interesting.
Look at the aspirations of STOA, the wastewater treatment works to 2030. We are now 2020, and I would argue that STOA, that Holland has done exactly what was said in that report. So is that something? I mean, Laurie Reynolds is saying yes, 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 fantastic. So I think he's putting his hand up to get involved. I think it's more than possible. Decentralized plants, yeah, obviously with wastewater, it's going to depend upon nations, nationals, population density. In the UK, not really much of an issue. In the US, absolutely. So I think it's one of those things, and it's potentially something we can do through the IWA. It sounds, what do you think, Leiv? Yeah. Yeah. Quite possible.
Sure.
No, definitely. I think it is an action that needs to be taken. So unless there's any more questions, Mikkel?
I think still. I think still we need to work with you, all of us, for better education. You know, higher education level at the wastewater treatment plants, especially the bigger ones, because that will be needed in the future to balance all the demands. It's not done by real-time control in a black box. We also need the know-how around it. So someone to look at the visualization of all the beautiful work
key, and I don't see enough of it.
Done.
It's something certainly I try and get organised in the UK, and one of the things we're trying to do is an international instrumentation apprentice competition, which feeds off a competition that WIPAC gets involved. WIPAC organises in the UK, but certainly if there is any interest on the international front for an instrumentation apprentice competition, which is going to be difficult considering. Well, it's difficult at the minute because of the state of the whole events industry and the pressures it's under. But any big instrumentation go.
Yeah, we have actually developed a little challenge on that using models. So we put all kinds of faults into the model, and then people have to find them. So
I think I was just about to wrap up anyway, so we are about half an hour over, but thank you very much to all of our speakers. I think there's been a great engagement today. This has been recorded, so those of you who've had problems with the technology, it will be on YouTube probably next week now. But thank you to all our speakers. It's been an absolute pleasure. And I hope you have all enjoyed it. Keep an eye out on the WIPAC group. Keep an eye out on YouTube, the WIPAC YouTube group. There's lots of videos there of all the previous webinars as well. So thank you very much to all our speakers. A virtual applause. And take care, everyone. Thank you.
Thank you, Oliver.
Thanks, everyone.
Thank you all.
Thank you, Oliver.
Glad you enjoyed it, Howard. Glad everyone enjoyed it. Thank you for everyone for joining. And keep an eye out on the WIPAC group for the recording of the event. Take care, everyone.